Fixed magnetic molasses. So the purpose of this lab is to study Faraday's law and Lorenz's force and the other ones for the motion of a bar magnet falling through an aluminum tube. So we used the magnetic field of a dipole, Faraday's law, Lenz's law, and Lorentz force. Experimentally, the time it took for the bar magnet to fall through the tube was 1.4 seconds, but computationally, it was found to be 1.768 seconds. So these are the main equations that we use. First of all, the magnetic field of a dipole, which you use from lab 4. Also Faraday's law saying the change in magnetic flux for the change in time is EMF around a closed loop. And then also the Lorentz force for a wire. We also use the definition of magnetic flux, the definition of resistance, Ohm's law, and Newton's second law for other steps in the experiment. The reason we do this is because we treat the bar magnet as a magnetic dipole, and the aluminum tube is a collection of rings. And our assumption is that the only change in magnetic field is the bar magnet, and the only thing that's changing is the magnitude as you fall through the tube. The bar magnet falls upright through the tube. The aluminum tube can actually be approximated as a series of rings, and the air resistance is negligible. So for the experiment, the system is the bar magnet, the tube, and the earth. And our initial conditions are just at rest. And so we just drop the bar through the aluminum tube and record the time that it took to travel through it. So here's a video. As you can see, it took around 1.4 seconds, a little bit slower than just dropping it normally. And so we tried to model this scenario using the glow script. So for the bar magnet, we found from lab 4 the magnetic dipole moment to be 6.78, the mass to be 0.033 kilograms, and those are the dimensions of the aluminum tube. And once again, we start at rest. So for the code, we first modeled the bar magnet into as a series of rings, and then used the function from lab 4 to determine the B field, and then use that to calculate d flux over dt using the expression that was found in the video. And then we also found the current using the induced EMF and Ohm's law, and then using that found the force using Lorentz force and the expression that was derived in the video. And then you just calculate the net force and update the motion to model the bar magnet falling through the tube. So here are the results. As you can see, the different colors represent the different direction of current. So at the top, it's going one way. At the bottom, it's going the other way. And as you can see, this initial drop off in velocity is when it was outside of the tube, so that's kind of negligible. But now what's interesting is that the velocity slowly slows down until it levels off when you're in the tube, and then once it's out of the tube, it increases again. So overall, it took 1.768 seconds for the bar magnet to fall through the tube in the computational model. And so as a result, we saw that the bar magnet falls slower through the tube in both cases, and it appears as though the velocity becomes constant. The increasing B field generates an increasing current, which generates a B field in the opposite direction, which causes the bar magnet to move upwards, essentially. Kind of think of it like two magnets back to back. So that's why, as the velocity increases, the force also increases until it reaches an equilibrium. It's worth noting that took slightly longer computational model is around zero point 0.3 or zero point zero 0.04 seconds of difference. Um, and this could be due to factors such as that the bar magnet was only upright at all times in the computational model, and that maybe there were other magnetic fields we didn't consider. And the observation is sufficiently large to consider the bar magnet as a dipole at a large distance. The tube can also be approximated as a series of rings. So here are the final values that we got. So the error is probably because it didn't fall perfectly. Error is not legible. The physical constants were measured with perfect accuracy, including such as like the dimensions of the tube or the dipole moment of the bar magnet, as well as human error while timing. So if the conductor was reduced close, if the resistivity of the conductor was reduced to as close as possible to zero, then that would happen, the resistance would also go as close as possible to zero. And so by Ohm's law, we say V equals IR, so that would correspond to a much greater induced current. But the induced current would also correspond to a greater force, since force equals, IL cross B, or the magnitude is IL B sine theta. So a greater force would further slow down the falling bar magnet, and it would just take a long, long time for it to fall through the tube. And there are also other things that you can change to ensure this. On the other hand, if we cut holes or slots, what would happen is that the ring currents would no longer form in these, specific sections of the tube where the holes or slots are. I guess there could be special cases where you could cut a hole such that the current still flows, but the resistance decreases, which in which case have an opposite effect. But if we're just considering the holes themselves cut across the tube, it would reduce the amount of like currents flowing across the aluminum, which would reduce the force and minimize magnetic braking effect. So it would take a shorter time for the bar magnet to fall through the aluminum tube. So in conclusion, it looks like Faraday's law and the lens force accurately model and explain the phenomenon of the bar magnet falling through the tube. The difference, was 1.4 seconds versus 1.768 seconds, which is significant, but it's also reasonable considering the error that was introduced through procedure. And then it's also worth noting that the speed at which the bar magnet falls depends on multiple factors, such as the bar magnet's mass, the dipole moment, as well as the dimensions of the tube. Thank you.